Hello friends, this is Om Prakash Samandre, Assistant Professor in CSC. We are discussing database management systems. In this video, we will discuss the BTree. A BTree of order M is also known as your M-way tree. Here the order is M. It must have the following properties. All the leaf nodes of the BTree must be at the same level. All the non-leaf nodes, means the internal nodes, except the root node, must have at most m number of values and at least m by 2 children. Okay, at most or maximum m children. Okay, not values, m number of children and minimum m by 2 number of children. Suppose the value of m is 4, then maximum 4 children should be there to the all non-leaf nodes, and a minimum 4 by 2, that is 2 children. Minimum 2 children, maximum 4 children must be there if the value of m is 4. The number of keys, that is the values, is 1 less than the number of children. So if you have 4 children, then the number of values that can be stored in the node is 4 minus 1, 3. Right, a node can contain 3 values, then it can have 4 children. Right, the sorry, non-leaf nodes and at most m minus 1 and at least m by 2 for the leaf nodes. So at least m by 2 for the leaf nodes, and for the non-leaf nodes the number of children, number of keys can be m minus 1. See, in the second point we have discussed the number of children. The third point we are talking about the number of keys, right? And the fourth one is the root may have as few as 2 children unless the tree is the root alone, right? So these are the four properties of the B tree. This is an example where the m is 5, order of the B tree is 5. If the order is 5, then all leaf nodes must be at the same level, that is always correct, and the number of children of the non-leaf nodes except the root node must maximum is 5, minimum is 5 by 2, that is 2. Okay, 5 by 2 is 2.5, so the lower value is 2, so 2 can be taken here. The number of keys is 1 less than the number of children for the non-leaf nodes. How many number of children can be present in the non-leaf nodes? That is 5. So 5 minus 1, 4 number of key values can be there in the non-leaf node. Similarly, a minimum number of key values is 2 for all the leaf nodes, right? The root may have as few as 2 children, that is also similar to the previous property. So these 2 points you need to keep in your mind, point number 2 and 3, and all the leaf nodes are at the same level, that is always correct. So this is one example of creating a B plus tree using these key values A, G, F, B, K. These are the key values, and here the order is 5. I can say first you consider the first value A, B, Z, F, because order is 5. The number of values can be stored in a node is 5 minus 1, 4. So first 4 values are stored here using the binary search tree property. B is larger than A, that's why B is placed in the right side. Again, F is larger than B, so F is placed in the right hand side, and so on. Now the next value is K. Can you place K here? Can you insert K in the first node? If you insert K here, then it will contain 5 values. and the order of the tree is 5. It can contain maximum 4 values in a node, so you cannot place k here. So if you place k here, 5 values will be there, so it will violate the property of the B tree. Hence you need to split it. We have split it from in the middle, so f is the middle one, so f become the root here. A B goes to the left hand side, Z K goes to the right hand side. Now the next value is D. D is smaller than F, larger than B, so it can be placed in the right hand side of B. Similarly, H is larger than F and greater than G, so it is placed in after the G. M is larger than F and larger than K, so that's why it is placed to the right of the K. Now when you are trying to insert J here, J is greater than H, lesser than K, so it is supposed to be placed between H and K, right? But this node already contains the 4 values, so if you place J here, it will the number of values will be 5, which will violate the property of the B tree. Hence you have to split in the middle of the node. So J is the middle value, so you can split like this. Okay, when you split, J will come here, GH will go to the left of J, KM will go to the right of J, but all the leaf nodes must be at the same level. That's why you can place J to the root node. You can place J to the root node, so that to the left of J, GH will be there, to the right of J, KM will be there. In this case, the leaf nodes are at the same level. Now E is placed here, there is no problem inserting E. Similarly, inserting SIR, there is no problem inserting SIR, because still these nodes containing only 4 values here, 3 values here, still one more is possible here, and this contains 4 values. Now when you insert X, X is larger than S, so X is supposed to be placed here. If you place X, again number of values will be 5 here, so it will violate the property. In that case you have to split. So again, when you split this, you'll get R to be moved to the root node, right? So you'll get this one. When C is to be inserted, when you insert C here, after the B before D, again it will contain 5 values, so you need to split that. It goes to the middle value goes to the root node. Again, when L is inserted, you can see inserting L is not a problem, because it can be inserted here, KLM. Similarly, N can also be inserted here, can be inserted easily, U also inserted easily, because without splitting and without merging, these number values can be inserted here. While inserting P, P is greater than J and lesser than R, so P must be inserted here after N. So when you insert P here, then it will have 5 values will be there, so again it will violate the rule of B tree, so you need to split at M. When you split at M, M should be sent to the root node. So root node already has 4 values, 5 values will be there. When M will go there, it will become 5 values. Again it will violate the rule of B tree. Again split should be done at the middle. So when you move M to the upper level will contain 5 values, maximum 4 should be there, so again at J you have to split. So J you have to split. So all the leaf nodes are at the same level, and you can see this is the B tree we have created, right? So you will definitely get a question about B tree creation or insertion of the key values or nodes into the B tree. That may be one question. Or similarly, you can also delete. Suppose you want to delete the value E. So E is deleted here, right? So deleting from the leaf node is very easy. So you can see E is deleted here directly. Okay. Or borrow from a neighbor. So when you deleted E here, you can borrow a value from the neighbor. So what is the neighbor here? Who are the neighbors? Neighbors are AB and GHI. They are the neighbors. So you can borrow the value from the neighbors. So G, you can place G can be moved to this place. F can be moved to this place. So that the minimum number of nodes, it must satisfy um, all the rules of the B tree. Minimum number of values must be 2. That's why you cannot place D here. So you should bring some value from the neighbor nodes. So here the neighbor node is this one, which contains more values. You cannot take the value from the left hand side neighbor, because when you take the value from left side neighbor, again it will contain only one value. It will again violate the rule of B tree. So from the right side you have to take the value. So from the right side, if you can take the G can be placed here, F can be placed here, so that it will satisfy all the rules of B tree. Similarly, delete the value F. Now where is F? You find F, yeah, from this tree. When you delete F, right, you will get this one. Now where to borrow? You cannot have only one value in the leaf node. At least two values should be there in the node, and both the neighbor are also having only two values. You cannot borrow the value from the neighbor. In that case, what you need to do, you have to combine and push the problem up one level. Now you can see this D, Z, H and I, these are combined here. So D, Z, H, I, these are combined here. Okay, and these are kept in one node, which is to the right side of C. And now again C must contain at least two values, and it should borrow from the neighbor. Again neighbor contains only two values, so again you can do the same procedure. Combine CJMR, become a single node here, CJMR. So the problem is pushed up one level. So CJMR become one node here, right? Similarly, when you want to delete M from a non-leaf node, in the previous case we have deleted the value from the leaf node, but here you can delete the value from a non-leaf node also. So in that case, immediate predecessor in non-leaf is always in a leaf. Immediate predecessor, you have to consider the immediate predecessor in the non-leaf is always in a leaf. So you can see the immediate predecessor of M is there in the leaf node. So in that case, when you delete M, then you can overwrite the M with its immediate predecessor L. You can see here immediate predecessor is L here. So in place of M you can place L. So I'll get this position. Right now, again, if you see it contains only one value, the leaf node should contain at least two values here. So that's why you can borrow the value from its neighbor. Its neighbor contains four values, so you can borrow the value. So it will become, you borrowed the value j, so it become jk. In this way you can borrow. J is borrowed here, I is placed here, the immediate predecessor is placed here, j is borrowed to the right side, so that the binary search tree property can be preserved, right? So this is the situation after deleting that M, right? So in this video we have learned how to create the B tree and how to delete the nodes from the B tree. In the next video we'll discuss what is a B plus tree and how it is different from B tree. Thank you very much.